talking about parallel vectors. How about the cross product of a vector by itself? What is the value of this? I know that the cross product is results in a vector, but what is the vector that results from the cross product of a vector by itself? Let's do the math and check it. I know that I'm going to put the first row, the standard unit vectors, ijk. The second row will be the components of my vector. The third is I'm using same vectors, so I have the same components. Now, if I do the definition of the determinant, or apply the determinant here on this case, on these values, I'll obtain array I. Then I'll end up with a 2 by 2 matrix, which is A2, A2, A3, A3, and by the minus J, and then I'll have the K. Okay. Here it will be A1, A1, A33, when it will be A2, A2, A1, sorry, A1, and A2, A2. Now it's obvious, I think you already saw it, that the determinant of these 2 by 2 submatrices that I'm seeing here, each one of them is a 0, and I have a 0 here, a 0 here, and so on. If I have a 0 vector that has these 0 components everywhere. Yeah, but the cross product of a vector by itself actually is equal to 0. Okay, now we know this information. But what if our vectors are parallel? If I have two different vectors, but I know that I know that they are parallel to each other. From our information before, we know that if a vector parallel to another one, then it is a scalar multiple of this vector, where C here is a scalar. Okay, the C is a scalar. So can you use the above information to determine what is the relation between two parallel vectors and the cross product? Substitute, I'm doing the cross product, let's write it here. I'm gonna do the cross product of A cross B, knowing that B is a scalar multiple of A, and knowing that they are parallel. Now I'm doing A cross, where B is C times A. C is a scalar, so I'll take it outside, so I have A cross A, okay? Then I'll end up with C A cross A, which is a 0 vector. So this tells me that if I have two parallel vectors, then the cross product also is equal to 0. If I have this theory, it's written already here on my slide. Yeah, but now we look at this corollary, tells me that if I have two non-zero vectors, one definitely non-zeros, because if any one of them is a 0, I'll end with a 0, and the 0 has no direction and they're not parallel. So the condition here, if I am talking about two non-zero vectors parallel, then if and only if A cross B. If and only if tells me it goes both ways. If they are parallel, then the cross product is a 0. If the cross product is 0, then they are parallel. Yeah, but this is another approach for finding whether two vectors are parallel or not. Okay, now let's do further. But I want to find another definition for the cross products, like we did with the dot product. But now I can't find the length of the cross product. Actually, the proof of this relation, we can do it here. It's long, but I'll give you just an idea what is the how we can do this. The proof idea of this proof, we're gonna start with the A cross B, okay? And we know that the A cross B actually is a vector. Let's start with A cross B without these signs, okay? The A cross B, I know it is a vector that consists of the components of the vector. Let's write it in the first definition, not the determinant form. Let's write it using its components. And now my A2, B3, sorry. Let's write it in component form. This actually will be A2, B3, and so on. Minus, go back to your definition at the beginning of the lecture. We have here A3, B1 minus A1, B3. Let's do it in one slide كده. A1 B3 وهنا A1 B2 minus A2 B1. Okay. Now we need to look at the length of this vector. That is, I'm gonna take the square of the components, add them up under the square root. But the first term there, this is my one, I'll get it here squared plus the second term squared plus the third A component of mean A squared. I will simplify these terms, okay? I won't do it well, you can say that, do it yourself. You're gonna expand these squares under the bracket. Definitely it will be A2 squared, B3 squared minus A2, A3, B1, B3 plus A3 squared, B1 squared, and so on. Add up the components, combine them together, or do grouping. Actually, you will end up with the magnitude of A times the magnitude B times sine the angle A theta, okay? But I will arrive at this formula for the length of the cross product. Actually, it has a very nice definition. Actually, it has a very nice interpretation, and I'm going to use it in our applications. We see here from this figure that if these two vectors A and B, okay, if I want to look at the length of the cross product, what's the geometric meaning? I can see it in this figure. Now, let's write it again now. A cross B, this is length. If I remember, we're talking about length. That's why this is a scalar, a number. It's the magnitude A times magnitude B times sine theta, okay? B sine theta, when I look here at this figure, actually this B sine theta is the height of the parallelogram. This is the height of this parallelogram. And actually A is the base of this parallelogram. And the magnitude, this is the length of the base of the parallelogram. So I know that base times height of a parallelogram actually is the area of this parallelogram, okay? This is the area of parallelogram. So this is one of the applications directly. If I have two vectors starting from the same initial point, and I can state that the area of this parallelogram, if I completed the parallelogram of these vectors, the area of this parallelogram actually will be equal to base times height, or magnitude A times B, magnitude B sine theta, or in other words, it is the length of the cross product between the two vectors, okay? We could practice by worksheets on these ideas, okay? Now here we have some other properties that are going to be useful, definitely. The first one tells me that A cross B is equal to minus B cross A. But I notice here, I'll do some remarks about the properties. The first remark is that the cross product is not commutative, okay? You cannot commute the ordering of operation of the cross product. In other words, A cross B is not equal to B cross A, okay? Is not equal to B cross A. Is not equal to B cross. They are not commutative, okay? The second thing also, when I look here at the property number 3, I could distribute a cross product into the bracket if I have A cross B plus A cross C. It makes a big difference if I'm doing cross product from the left or from the right, okay? So when I do from the left end, the cross product A will come from the left. If I'm doing it C from the right, it will come from the right end, okay? So take care about this. Also, I notice here from these properties, I don't have the associative. Yani if I have A cross B cross C, okay, if I associate A cross B, I have A cross B cross C, I could associate this and this. Actually, it is not associative. But this property is not satisfied, and the cross product is not associative. How are you going to verify this? Actually, I need you to find a counter example that states that this statement, or an example, yani, to state that this is really not true. Okay. Property one, if you want to look at it in the geometry of property one, actually it means that the cross product, when I reorder A cross B or B cross A, actually this gives me a negative sign, which is logical. They will have the same length A cross B, but will have different orientation. Using the right-hand thumb rule, actually, when I go from A to B, I'll have my vector pointing up. If I'm going from B to A, I'll go the negative direction, then my vector will be pointing in the opposite direction of A cross B. So B cross A actually is the same length, but in the opposite direction of A cross B. Okay, this is property one. Also, you could talk a little bit about property property 5. Actually, property 5 tells me that A dot B cross C is equal to A cross B dot C. And this equality actually is valid. We call this triple product, we call it the scalar product. Let's see why. I have this bracket B cross C, vector cross vector actually is a vector, okay? This is resulting in a vector. A vector dot vector A, this is a vector dot vector. Actually, the dot product is a scalar quantity. So in the end, the triple product A dot B cross C actually is a scalar triple A product. So this property tells me I could alternate the order of operations. And I started with a dot, then cross, I could say cross, then dot. I could combine A and B, or I could combine B and C. Okay, these are all give me same ideas on condition. Even in addition to these relations, all are valid. These are all okay. On condition that I stick with the cycle or the direction, and I have A, then B, then I have C. You'll notice that all of these operations are moving in the same cycle, A, B, C, or B, C, A, or C, A, B. And they don't care about the order of operators. Dot will cross, okay? So this will be our positive direction, and they are all valid. Why is this so? What is the proof of this relation? Actually, the proof is simple using the determinants. We saw before that the cross product B cross C. Okay, let's look at this part of the vector. Okay, let's of the operation B cross C. We have seen that B cross C. What's happening now? Let's see, B cross C. Actually, when I want to do it, I'll say I, J, K. Well, then I'll put B, which is B1, B2, B3. While I will C, which is C1, C2, C3. This is the cross product, right? I'll do the job like this. Add the I times the determinant of the order 2, yani B2, C2. B3, C3, but minus J times this one بقى اللي هتبقى B1, C1, B3, C3 plus K, which will be the B1, C1, B2, C2. This is what I know from the definition of the cross product. Now I want to add up another operation to this, which is A dot B cross C. I already have the B cross C, no? All of this is my B cross C, and I want to dot product this with the A, okay? So when I dot product, what do? I know that my A is the components A1, A2, A3. To dot product, all you have to do is multiply corresponding components. If I have A in the direction, X direction, and I have this value in this direction. So I'll end up with A1 times this bracket. If A1 will be multiplied by this, if I'm going to replace the I by A1, if I'll end up with A1 times B2, B3, C2, C3. You got the idea? The other term minus, I'm going to multiply برضو corresponding components. يبقى I multiply A2 by the component in the y direction. يبقى بالتالي I'll have A2 times B1, C1, B3, C3, and so on. The third, I'm going to multiply A3 I3 by the third يبقى بالتالي I'll obtain this plus A3 times B1 C1 B2 C2. Undo بقى this grouping, actually I'll end up as if this was actually the determinant of a 3 by 3 matrix where the second row and the third row is B2 B1 يعني B2 B3 and the third row was C1 C2 C3, and actually instead of IJK I ended up with A1 A2 A3. But this is an alternative way to do the triple scalar product. And if I have three vectors, A, which is مثلا 1, 2, 1, and vector B, which is negative 1, 1, and 1, and C, which is 2, 1, negative 2. Okay, now I want to do triple scalar product. I want A dot B cross C. Okay, instead of doing B cross C, well, then I do the dot product. As I know from the before analysis, all I have to do is put them in my determinant in the order, in the same order they appeared in. A would be the first row, negative 1, 1, 1, 2, 1, negative 2. And I'll do the job like this. I'll end up with a scalar, which is the value of 1, negative 2, negative 1, negative 2 times 2 minus 2 plus 1 times negative 1, negative 2. Okay, yani I'll have this value, which is equal to negative 3, and that is a 0, with negative 3, yani, which is a negative 6. But this value is a scalar, definitely, and it gives me the value of this scalar triple product. So what does this 6 mean? What does the value of this 6 mean? Actually, I have this application that tells me that actually this is a volume. Let's see why is this the triple scale, the length of our, it's not a length, but it's a scalar. I know that A dot B cross C is a scalar, but it might be positive or negative. That's why this brackets, actually these are brackets of absolute value. Okay, so why is this the volume? Why is this scalar triple product is the volume? Let's see. V, I know the volume of this parallelepiped. Let's start with this parallelepiped actually is constructed from these three vectors. These three vectors are A, B, C, and they are starting from the same point. The our haga must be taken into consideration. So I started from here. I have this vector BC. Actually, they made me the area of this parallelogram. Actually, and this is the base of my parallelopipes, right? And where is the height of this parallelopipe? The height is this, the length of the height is this, okay? But what is the direction of the height? Actually, the direction of the height must be perpendicular to the plane that contains B with C. So actually, as long as the height is perpendicular to B with C, then the height is actually is in the direction of B cross C. If the height is in the direction of B cross C, I will say that the height is parallel to B cross C, okay? Now it is in the direction of this one, okay? So this height actually will be like this. So one height and the length. So I know that this length, let's do a more analysis. What is this theta? And I'll mention that this theta is the angle between the vector A actually and the direction of the height, which is B cross C, okay? But this is the angle between A and B cross C. So if I want the length of this segment of line, which I'll call it the height, actually this will be from this triangle, right angle triangle, it will be magnitude A times cosine the angle. Now it is the adjacent of the angles. This is adjacent, so it's a cosine. Hypotenuse, my length of A times cosine the theta. Now I have everything. We know from before the area of a parallelogram is the cross product of the two vectors. يبقى بالتالي B cross C. Okay, and I'll take the length. I'm talking about area. I don't need a vector. I need a length. يبقى B cross C. يبقى now I have the area of base and I have my height. So the volume of this parallelogram, or parallelopipe, sorry, is equal to area of base. مش كده؟ base area اللي هو parallelogram times LA height, which I called it H. Well, base area is B cross C as a length times the height, which is magnitude A times cosine theta. Now this gets me back to again to the definition of the dot product. If I have a dot product between two vectors, but it is equal to the magnitude, the product of the magnitudes times cosine the angle theta between them. Is this theta the angle between A and B and C? Yes, we have just saw it from figure. Theta is the angle between A and B cross C. That is why the volume actually will be B cross C, okay, dot product within A, and A dot B cross C, okay. Now we notice something. We know that volumes must be a positive values, and this cosine, and I know my theta might range from 0 to pi. So to have positive values, actually I should add here an absolute value. يبقى بالتالي I need هنا my cosine theta be always positive because I'm dealing with volumes. يبقى I'll have absolute. يبقى ending up, يبقى the whole scalar product must be positive. So that's why I take the scalar triple, yani product must be positive. So that's why I take the absolute sign here after all, okay? Exercise in the worksheets. Thank you.